All right, so I'm Les. I work with the Student Success Center and peer tutoring. I specialize in math, physics, and statistics. I'm glad you're all back. And before we get started on the lecture today, we'll go ahead and look at some preliminary examples. Hopefully this will let us review two basic functions very important to calculus. So one of the functions is the exponential function, e to the x. Okay. Now, just a quick review. What is the domain of this function? Just looking at the graph, and I'm looking at chat. So for the exponential function, what are the all real numbers? That's right. You can plug anything into the exponential function, negative or positive. So it's all real numbers. And what is the range for the exponential function, just even by going by the graph? Okay. So we see that the graph of e to the x is always above the x-axis. So that means the range is all positive numbers. So e to the x is always strictly positive. Okay. Yeah, excluding 0, of course. Okay. But more importantly, we would like to look at the behavior of this exponential function for in the long term. So when x either goes to plus or minus infinity. So looking at the graph, as x goes to negative infinity, what do we see the values of our exponential function going to? Okay. Now this might be too basic for some of you all, so maybe that's why you're not typing in chat. But as x goes to negative infinity, our exponential function, if we look at the graph, goes to 0. Thank you. Okay. So as a limit statement, we would write the limit as x goes to negative infinity. So x gets arbitrarily negative. The function e to the x then approaches 0. So at the limit, it's 0. Okay, so what about the other side, the other long-term behavior of our exponential function? So as x goes to positive infinity, we see that our exponential, as advertised by the name exponential growth, blows up. So as x goes to positive infinity, e to the x goes off to infinity. So we would write the limit as x goes to positive infinity of e to the x at the limit is equal to, well, it's infinity. The function grows without bound. Okay, so those are important things to know about the exponential function in terms of limits, right? How it behaves when the argument is negative infinity, that will be 0, and I'll put that in quotes because that's really there's a limit statement behind that. And e at infinity would be infinity as a limit. Thank you. All right, so the other important function, of course, very much related to the exponential is the log function. And it's important because, well, it's related to the exponential because they're inverses of one another. So here, we first look at the limit as x goes to 0 from the positive side, okay? So can somebody in chat say why this wouldn't make sense? Why wouldn't we consider the limit as x approaches 0 but from the negative side? Yeah, so we see that the domain of log will be exactly the range of the exponential function, but it's only positive numbers, positive real numbers, but the range of log is just the domain of the exponential, so it's all real numbers. Okay. So of course, log of a negative number, even if it's close to 0, makes no sense. So we can only really talk about the limit or the behavior of log as x approaches 0 from the right. And we see the function blows down, right? So the log of x as x goes to 0 goes to negative infinity. So we would write the limit as x goes to 0 from the right of log is negative infinity. Okay, and finally we see that as x goes to positive infinity, doesn't grow very fast, but log does grow without bounds. So as x goes to infinity, log of x goes to infinity as well. It grows without bound. Okay, perfect. So that's just a warm up, just to get a kind of sense of how your two basic functions important to calculus behave in terms of limits. Okay, and we did this so that we can so this introduces the two types of things we're going to be talking about today. One are limits at infinity, right? Limits at infinity are describes the long-term behavior of the function as x to negative infinity or positive infinity, right? So we looked at three limits at infinity. And the other thing we'll be looking at are limits that are infinite. So x could be approaching some finite number, for example, like in this log, x goes to 0. But the function itself either goes to negative infinity or plus infinity. So those are infinite limits. So limits at infinity, so that's when x goes off to plus or minus infinity, and infinite limits when the limit itself, when the function goes off to plus or minus infinity. And to deal with such things, we maybe look at a prototypical function again. F of x is 1 over x. And you should be able to describe the asymptotic behavior here. So limits at infinity, x goes to plus or minus infinity. And we see that according to the graph, as x gets very positive or very negative, the value of the function will approach 0. Okay, so so looking at this prototype, you'd like to think of this as saying that if we have some non-zero number, that's going to be the important, I used 1, but it's any non-zero number, divided by something that goes to plus or minus infinity, is something that goes to 0 at the limit. So as a metaphor, I know some of you have been talking about shedding tears over some of the problems. Well, the metaphor would be like the number on top is a tear and the number on the bottom is the ocean. So one tear in the ocean is nothing, right? Okay, so that's the joke. Okay. Now, infinite limits we can find in this graph as well. So we see that as x approaches 0 from the left, the negative side of the number line, the values of the function decrease without bound. So we say that 1 over x goes to negative infinity as x goes to 0 from the left. So a non-zero number divided by something that goes to 0, but from the left, so that's a slightly negative 0, so to speak, is something that goes to negative infinity. And finally, we see that as x goes to positive infinity, then we get something like a finite number over something that goes to 0 but is slightly positive. That's something that will go to plus infinity at the limit. Okay. So we have the limits at infinity. That describes where x is going. And then we have problems where the limits themselves, the y values of the function are infinite, plus or minus infinity, so infinite limits. Those are the two basic problems you're going to be looking at today. We'll also have a third topic, which is the squeeze theorem. Okay. So let's go ahead and look at limits at infinity first. All right. So limits at infinity will describe the behavior of a function as x goes to plus or minus infinity. So how the function behaves in the long run, to the right and to the left. So as we saw with the exponential function, the long-term behavior, the limit itself might be, well, infinity, right? So here exponential function blows up as x gets very positive, or it might get we might get a finite number. So as x goes to negative infinity, we would get the 0. Okay, so we can get an infinite limit or a finite limit. We could also have it that the limit simply doesn't exist in the sense of the values of the function in the long run not settling down at all. So of course I'll use the sign of x as a prototype. And it doesn't matter which way you go. So you gotta have faith that that's the graph of sine of x. Okay, so here we see that as x goes to infinity, sine of x, well, sine of x we know just keeps oscillating, right, between negative and positive 1. So the number, the function's value never grow without bound. They never settle to a single number. The limit here simply just does not exist because sine of x keeps oscillating. No difference. There is no difference if we let x go to negative infinity. Yeah. So the limit might be infinite, might be finite, or might not exist. Okay. So we're going to look at how to, oh, I forgot to define horizontal asymptote. Okay. So the asymptotic behavior of a function is, well, it's long-term behavior as x goes to plus or minus infinity. And if that long-term behavior of the function is that the function approaches a finite number, okay, the picture might be something like, here we have a horizontal line. So that on that line, the x coordinates are constant. So y would be L and x doesn't matter. But the long-term behavior is that as x goes to infinity, the value of our function approaches a single value. So if you'd like a horizontal line. And we might have that the function approaches a finite value if we instead let x go to negative infinity. So x goes, so it's like the long-term behavior of the function. I don't know. Okay, but in either case, as long as either the limit as x goes to infinity or minus infinity is a finite number, then we say that our function is approaching the value, constant y value, and we call that a horizontal asymptote. So we say that f of x has a horizontal asymptote if and only if what either limit right, so either if the limit from to the right is L or to the left. So now the limits from a function might have more than two or more than one horizontal asymptote, and we'll see examples of that. So when checking for horizontal asymptotes, what you want to do is compute the limit as x goes to infinity and check if we get an asymptote that way. And then also you have to find the limit as x goes to negative infinity, because you might get no asymptote that way, or you might get a different one or the same one. But you have to check both infinite limits. Okay. And let's look at the, this is the, we're going to look at some of the algebra you want to do when evaluating infinite limits or checking for horizontal asymptotes. And this is the, this is algebra, so it's pre-L'Hopital's rule, if you know that. So this is what you want to do if you weren't allowed or didn't know L'Hopital's rule. So what we want to take advantage of when finding infinite limits, sorry, limits at infinity, is the fact that if you have, again, a non-zero number divided by x, and in fact any positive power of x, could be x squared, right? X cubed, it doesn't matter. We see that this will go to 0 as x goes to plus or minus infinity. Again, the idea being that you have a fixed numerator, but the denominator grows arbitrarily large, so you get something that approaches 0. Okay. So here, in this problem, we want to take advantage of this fact, right? And here's, notice we have exactly a single term in the denominator, so we are free to go ahead and divide each term in the numerator by that single term in the denominator. We'll do the quick algebra here, the cancellations. Okay, now, oops. So why is this useful for our problem of calculating the limit as x goes to infinity, right? Well, because notice that we have either a constant term, which is unaffected by what x is doing, right? It doesn't care. It's just a constant. It remains itself as where x, regardless of where x is going. But the other terms that have an x in the denominator will definitely go to 0 as x goes to infinity. So that's the main idea in computing these limits pre-L'Hopital's rule, right? We're just going to get the limit of the constant as itself, but the limit of the terms that have an x in the denominator is 0, because x is going to infinity. So here we see that the limit is 2. So the idea here is to rewrite everything so we have either constants or constant divided by some positive power of x. So it's easy to evaluate the limit as x goes to plus or minus infinity. Okay. So we see that, by the way, since the limit of our function as x goes to infinity is a finite number, we say that y equals 2, which is a horizontal line, is a horizontal asymptote. Where did the 3 and 1 over 3 to 3? Oh, thank you. Somebody mentioned that I made a typo here. I forgot to bring down the 3. All right, so I'll go ahead and move on to the next example. So here, again, we're looking for horizontal asymptotes, right? I'll just call them HA. So we know that in trying to see whether these horizontal asymptotes exist or not, we're going to have to compute 2 limits. Okay. And we'll use exactly the same idea we did in the previous problem, except this time we don't have just a single term in the denominator, but we have 3 terms. But again, what you can do is simply look for the highest power of x. Now, this is not the only way to do it, but it's a set way. So find the highest power of x. Let's say in the denominator. Okay, and then we can divide the top and bottom of our fraction, and yeah, by that highest power of x, and then evaluate the limit if possible. Again, the idea being that we want to have constants and then constants over some power of x. Okay. So let's find the limit as x goes to positive infinity. And I see that the highest power of x in the denominator is x squared. So I'll go ahead and divide the top and bottom by x squared. Now, how do we know that we're not dividing by 0, by the way? Right? That's the one thing we can't divide by is 0. So how do we know that x is not 0? How do we know that when dividing by x squared, we're not dividing by 0? How do we know we're not dividing by 0? Yeah, thank you. A very simple observation is that, as x goes to infinity, well, clearly x is going to be far away from 0, so x is going to be greater than 0 in this case. So it's non-zero. Okay. All right. So then we divide each of the terms in the numerator by x squared, and I'll spare you the algebra. Okay. And the same thing in the denominator, divide each term in the denominator by x squared. So now we're ready to evaluate the limit. And here, it's very convenient, right? The constant stuff just remains constant at the limit because the constants don't care what x does. But anything that has an x in the denominator will go to 0. All these guys will go to 0. Okay, so we get 6 over 3. Okay, so we see that because the limit as x goes to infinity is positive 2, we see that our function has a horizontal asymptote. Okay, and now this argument would be affected if we instead let x go to negative infinity? Well, well, no, you would use exactly the same trick or the same technique. You find the highest power of x in the denominator, divide the top and bottom by that highest power, reduce, and then evaluate the limit, but the situation is exactly the same, right? Oops. So the constants will remain themselves, but all the other junk will go to 0 because x is going to negative infinity. So we still get 3. So again, that's we don't get a new horizontal asymptote. That's still the old one, y equals 2. All right. Any observations or questions about this? Yeah, so far we've been looking at functions which are rational functions, right? So polynomial divided by polynomial. And I know that you have some pre-calculus techniques for finding horizontal asymptotes, if any, right? But we want to use the calculus technique of computing infinite limits at infinity. So that way, if we start working with functions which are not polynomials or divided by polynomials, we have a more general approach. Okay, so here we're looking for horizontal asymptotes, if any. So we are going to look for the highest power of x in the denominator, and then here it won't matter whether we go to plus or minus infinity, so I'll just do both in one fell swoop. So the highest power of x in the denominator is x cubed. Okay, simplify the numerator and the denominator. Okay, so again, we see that all the terms that have a x or some power of x in the denominator will go to 0, and the constant will remain itself. So at the limit on top, we get 0. At the bottom, we get 2. Okay, so does that limit exist? Sure. 0 divided by non-zero is perfectly defined. It's equal to 0. So since this limit, and notice that it didn't matter whether x went to plus or minus infinity, right? So we have, since that limit as x goes to plus or minus infinity is finite, we get that y equals 0. So that's just the x-axis. It's a horizontal line. Is a horizontal asymptote of our function. Okay. So from pre-calculus, if you recall, we note that the highest power of x in the denominator is bigger than the highest power of x in the numerator. So in the long term, this essentially is going to act like, well, just you just focus on the highest power term. So it's going to be something, right? That's the kind of asymptotic intuition that you want to gain. What happens in the long run, and you just look for the highest powers of x. So our function in the long run behaves essentially like this one. So that's going to go to 0. Yeah, 0 divided by a non-zero number is 0. Okay. All right, so we are now going to jump to a more complicated example, unless you have questions on this. Hopefully the technique, the idea is that limits at infinity, pre-L'Hopital's rule. This is one method. Look for the highest powers of x and divide. All right, so this is a more complicated example because of a complication which you should be aware of. If you're not already, you will be. But it has to do with, so let's just do a little, before we look at this function, here the complication is that we have a square root. Okay, so before we tackle that problem, let's just focus on this expression, the square root of x squared. 1 second. All right. Okay. So what does the square root of x squared look like? What does this reduce to? Square root of x squared. Okay. So everybody says x. Okay. This is not completely right. So you know what? I'll just say it's wrong. All right. Well, it's not true always, right? So it's true that if you say square a number and you take the square root, and that number happens to be positive, you'll get that number back. Yeah, the square root undoes the squared. However, what would happen if you instead took a negative number, squared it, and square rooted? Well, negative 5 squared is positive 25, and the square root of 25 is defined because it's a function to return a non-negative value. So it's defined to be 5, right? So you see the problem. Here the original x value was negative 5, but squaring gave you a positive 25, and square rooting always gives you a non-negative number. So x is no longer, yeah, I know, this is picky, but it's expected in first semester calculus. Okay, so what we're going to say is that the square root of x squared is simply the absolute value of x, right? Because the squaring and the square root business strips away the negative, any negative part of x, if you will, just leaves the absolute value of x. Okay. So this is the correct way to simplify that. Square root of x squared is the absolute value of x from now on. And then we can trade that in for a piecewise function. Okay. That is to say, if x is positive, or say not negative, so positive or 0, then we can simply drop the absolute value bars, right? Because x is positive in the first place. Okay. On the other hand, if x is negative, then if you drop the absolute value bars, you have to negate that known negative to get the positive that you would if you were taking the absolute value. So that's an important thing that you want to think about, explain to yourself or your friends why that is. And that's the correct algebra. Square root of x squared is the absolute value of x. And then we can trade that in for cases. If x is positive, then you just drop the absolute value bars. If x is negative, you negate that negative x to give you what absolute value of x would. Okay. All right. So with that interlude, so this is the correct now. Let's now find horizontal asymptotes, if any, of this function. So we are going to find the limits at infinity. So first plus infinity. Okay, so here I'm going to look for the highest power of x. Let's say it's underneath the square root. So maybe instead of dividing, right, I'll just think of it as just factoring out an x squared. So inside the square root, after we factor out x squared from the first term, we're left with 1. From the second term, we'd left with 3 over x. And the last term, we'd be left with 4 over x squared. And from top, on the top, I'll just factor out a 5. Okay, so at this point, you have to stop me if you don't understand what just happened, how I factored out, and how I knew what was left behind inside the parentheses after, like, counter distributing, so to speak, right? Okay. So this is where we have to apply this idea that the square root of x squared, right, is not just x, but it's the absolute value of x. It's going to make all the difference in the world, right, if you want to get full credit. Okay. All right. So if you look at x over the absolute value of x, how do we simplify this in this problem? Well, we know that the absolute value of x is going to be just x. Why? And you want to justify this if you're communicating with your grader or professor? Because x is positive as x goes to positive infinity. Right, so since x is positive, just drop the absolute value bars. Okay, once we do that, we see that we do have x divided by x is positive 1. And now we're ready to compute this limit as x goes to positive infinity, because all the terms go to 0. All the terms that have a power of x in the denominator go to 0, but the constants remain. So we get that the limit is 5. Okay. So since the limit is finite, we say that y equals 5 is a horizontal asymptote. And I heard some sort of thank you. Thank you, Elliot. I forgot to write down the square root. It doesn't change the answer, but okay, sorry for that. Okay. All right. So now let us compute the other infinite limit. So let x go to negative infinity, because we always need to check the limit might be different or might not exist. Okay, now we would start off the same way. Okay, just factor out a x in the numerator and then an x squared inside the square root in the denominator. But what's different now is that we're letting x go to negative infinity. So we know that square root of x squared is the absolute value of x, but since x is negative as x goes to negative infinity, we have to use the fact that that will reduce to, the absolute value of x becomes the negative of x, right? Because x is negative. So negate the negative to get a positive. So you see how this divided by that will simplify differently now. Right, so we're getting an x over the negative of x. Okay, so now this will reduce to not to positive 1, but to negative 1. A number divided by its negative is negative 1. Okay, but now we have constants, and then constants divided by powers of x, so we're free to evaluate this limit at infinity. So we're going to get negative 1. This goes to 0, that goes to 0. So we're left with negative 5 this time. So the limit as x approaches negative infinity is now a negative 5, whereas as we let x go to positive infinity, it was positive 5. So we get a different horizontal asymptote. Okay. Okay. So that's something that will be thrown at you before L'Hopital's, I guess. And this is the thing they expect you to know, the algebra. All right. So, okay, so that's limits at infinity. If the limit as x goes to plus or minus infinity is a finite number, then we get horizontal asymptotes. Y equals that number. Okay, so now we're going to look at infinite limits. So this is going to be where the function's values go off to plus or minus infinity. Okay, so let's just look at a definition. All right, so if x is approaching a number, let's say in this picture is going to be from the right, and the function either goes off to, it grows without bounds, so it goes off to infinity. We call that an infinite limit. So in the picture here, as x approaches a from the right, according to the graph, the values of the function grow without bound. Okay, so we say that's an infinite limit. So the function goes off to positive infinity. Okay. And in this picture, we see also that, well, let's do that later. So if instead the function decreases without bound, so it gets more and more negative, then we have a negative infinite limit. So we would write limit as x approaches a either from the left or the right. In this picture, it's from the left. The function here decreases without bound, so we say the limit is negative infinity. Okay. And as x approaches a, let's not do this problem. So to define a vertical asymptote, as long as one of the one-sided limits, so x could be approaching a from the left or the right, at least one from one direction. If one of those limits is plus or minus infinity, then we have a vertical asymptote. Okay. So as soon as one of the one-sided limits is plus or minus infinity, we have a vertical asymptote. Okay. So when asked if we have a vertical asymptote for a function, you want to look for discontinuities. I shouldn't use that word. Hold on. to find vertical asymptotes. Okay. Number one, look for discontinuities, as I said, but maybe that's a bad word for now. So instead, let's say look for where the denominator is 0. Okay, and those give you candidates for where we have vertical asymptotes. I'll just call these VA from now on. Okay. And then compute the two one-sided limits. To see if one of them, at least one of them, yields plus or minus infinity. Okay. And if at least one of these limits is plus or minus infinity. Then we say that x equals a is a vertical asymptote. Okay. All right, so that's just a quick definition. To find horizontal asymptotes, you look for where the function is discontinuous. For our purposes, it's just where the denominator is 0 for now. And then you computed the one-sided limits, and if at least one of those one-sided limits gives you plus or minus infinity, we can conclude that we have a vertical asymptote. So here we're going to, for the first example, we're going to look for horizontal asymptotes. So here the function is going to be undefined whenever the denominator is 0. So let me go ahead and factor that denominator. Okay. And so this function would be undefined or have discontinuities whenever the denominator is 0. So we have candidates for vertical asymptotes. Okay, we have x equals -5, and then we have x equals 4. Okay, so let's consider x equals, I guess, 4. Okay, so we would compute the one-sided limit. So we're going to let x approach 4. Let's say from the right. Okay, and we see that if we try to evaluate directly, the numerator becomes 16 minus 16. The denominator becomes 0 as well. So that's an indeterminate form. So we need to do some algebra. And if you learned the algebra from yesterday, or you were reminded of the algebra yesterday, simply factor. The numerator is the difference of two squares. So that factors into a product of conjugates. Okay, so we have a cancellation. The x minus 4s cancel. And now we can evaluate directly. We get 8 on the numerator, and then we get 9 in the denominator. So that's not an infinite limit. Okay, but you should check also from the left. You're going to be asked to justify whether you have a vertical asymptote or not by looking at the one-sided limits. So you would have to compute them both. Okay. And that doesn't change anything, right? Because we still get that x minus 4 cancellation, and then we get 8 over 9. Okay, so that's finite. So here x equals 4 is not a vertical asymptote because neither of the one-sided limits was infinite. Okay. So now we would want to check as well at x equals -5. And so the same procedure, check the one-sided limits. So we approach -5 from the right. We already say factored and simplified. Okay. So now we have to see that the numerator goes to -5 plus 4. The denominator goes to -5 plus 5. So you get -1 over 0, right? So you get plus or minus infinity, right? Anytime you have a non-zero number divided by 0, that's going to be an infinite limit. But what you have to be able to do is determine whether that infinite limit is plus infinity or minus infinity. So you might have to do some sign analysis here by using test points or something else. Okay. So the numerator is clearly -1, right? It's negative. There's no question. So it's negative. Nothing to analyze there. But the denominator goes to 0, and we want to know whether that quantity in the denominator that's approaching 0, whether it's slightly positive quantity or slightly negative quantity. So we can look at -5 on the number line. Note that that x is approaching -5, but from the left. So x is somewhere over here. So one way to think about this is that we know that since x is to the left of -5, x is going to be smaller than -5. Adding 5 to both sides of this inequality gives us that x plus 5 is negative. Okay. So x plus 5 is going to approach 0, but it's going to be slightly negative. Okay. Now, another thing you could have done is just look at the factor at x plus 5, choose a test point. So, for example, choose a value that's to the left of -5, like -5.1. If x is -5.1, then you get a negative number. So you can then imagine that x plus 5, where x is smaller than -5, is a quantity that's negative, because that the test value became negative. All right, so the numerator is -1. The denominator is approaching 0, but it's slightly negative, right? It's approaching 0 from the left. So -1 over -0, so to speak, is, well, positive infinity. Yeah, negative divided by negative. Okay. All right, so right away, because the limit, this one-sided limit, as we approached -5 from the right. Oops, I said from the left. I apologize. I was finding the limit as x approaches -5 from the left. So my notation was off. Okay. Since that limit is positive infinity, we see that x equals -5 is a horizontal asymptote. Okay. And, you know, we might as well go ahead and find the limit as x approaches -5, but from the right. So nothing would really change except the sign analysis here, where the numerator goes to -1. The denominator goes to 0, but as x approaches -5 from the right, x is somewhere over here, we see that x plus 5 would be positive, right? So if you'd like, x is bigger than -5, add 5 to both sides of the inequality, and you get that x plus 5, this factor, is positive. Also, you can choose a test value, like -4.9. So our test value confirms that we get something that's becoming small, but is still slightly positive. So the the denominator is approaching 0 from the positive side. So you have -1 divided by a slightly positive 0, so at the limit, that would go to -infinity. Okay. Anyway, but it doesn't matter, right, in terms of the vertical asymptote. As soon as one of the one-sided limits was plus or minus infinity, we already knew that we have a vertical asymptote. Okay, how much time? Okay, perfect. I'll move on. I think I exhausted that example. Yeah, let's go ahead and do this one. So here we're looking for horizontal asymptotes. So I'm going to look for where we have the function being undefined. Now the numerator, by the way, we have a square root of a perfect square. So x minus 6x plus 9 does indeed factor into a perfect square. The denominator we can also factor. I believe, what is it? How does the... what does the denominator factor into? So yeah. Okay, there you go. That fixed it. There you go. All right. All right. So notice that the domain of this function is everything but x equals 3 and x equals 5, because that would make the denominator 0. So those are the two candidates. So what would happen if we approach 3 from the left? Well, the numerator we can simplify. What does the numerator simplify to? And I'll go ahead and wait for an answer in chat. Oops. Hold on. What does square root of x minus 3 squared simplify to? Thank you. Right, so that's the thing that we don't want to read. This is absolute value of x minus 3. Square rooting something squared gives you the absolute value of the thing. Okay. Okay, so how can we simplify the absolute value of x minus 3 divided by x minus 3 as x approaches 3 from the negative side? Okay, well, so it's the question, it's plus or minus, right, 1, but which one is it? It's not both. It reduces to either plus 1 or minus 1. So do we know which one it is? Okay. All right. So you agree that the numerator is going to be positive, not negative, right? It's going to be positive, right? Because it's absolute value, right? So here's 3 on the number line. X is approaching 3, but from the left-hand side or negative side of the number line. So if X is to the left of 3, would you say X minus 3 positive or negative? So X is to the left of 3. So X minus 3 must be, okay, so for example, X could be like 2.99. It's test value. So that X minus 3 would become 2.99 minus 3. So you owe somebody a penny, I guess. Okay, so it's negative. Okay, so the numerators, well, let's do it this way. Since X minus 3 is negative, the absolute value of X minus 3 is going to become the negative of X minus 3. Remember, whenever the argument of your absolute value function, okay, I need to get rid of that glitter marker. So if the argument of your absolute value is negative, then we get to drop the absolute value bars, but we have to negate that known negative to get the positive value that the absolute value does or would return. Okay. So this would be, all right. So we see that when we cancel, we get -1 in this case. So you get -1, then X minus 5. So at the limit, we get -1 divided by -2, so positive half. Okay, so that's a finite limit. It's not an infinite limit. And if we now approach 3, but from the positive side, or the right-hand side, we also want to reduce. But how does this reduce? Well, we're approaching 3, or X is approaching 3 from the right. So X could be like 3.1. Okay, so X minus 3, like 3.1 minus 3 is 0.1. So it'll be positive. So we can say that the absolute value of X minus 3 is simply X minus 3, since the argument of our absolute value is positive. So we just drop the absolute value bars. Okay. So now this would reduce to just 1. Okay. Uh-oh. Okay, so now the limit would be -1/2. Okay, so the two one-sided limits are both finite. Well, from the right or from the left we have positive half, from the left we have negative half. But anyway, they're both finite. So X equals 3 is not a vertical asymptote. No, all right. So we also have another candidate for a vertical asymptote at X equals 5 because that value of X also makes the denominator 0. So we compute the one-sided limits. Okay. Now, this will reduce to +1. Do you see why? Right. Well, X is approaching 5. So 5 minus 3 is +2. So both of these. Well, so X minus 3 be positive, right? So X minus 3 is positive when X is close to 5. Okay. So this would just reduce to, okay. So now we're going to get something that's like 1 over 0. So that we know that's an infinite limit. It's plus or minus infinity. It's your job to identify which one that is. Is it plus infinity or minus infinity? Well, so as x approaches 5 from the right, what can we say about x minus 5? Well, x is bigger than 5, so x minus 5 should be positive. If you'd like, you can choose a test value for x, like 5.1. So we get something that's approaching 0, but is slightly positive. So the numerator goes to 0, but from the right. So positive 1 over something that goes to 0 from the positive side. Positive divided by positive is positive infinity. So this one-sided limit was infinite. So we know that x equals 5 is a vertical asymptote. Okay, and the limit from the left, for the sake of time, I won't do that one, but the limit from the left, so x is approaching 5, but from the left would be negative infinity. Okay, so let's do one more. I'll let you think about this one. So if we're looking for vertical asymptotes, okay, for this function, e to the 1 over x, what is the candidate here? What's a candidate for a vertical asymptote? So which value of x is this function undefined? 0. That's right. Because even though that x, that 1 over x is in the exponent, dividing by 0 is still undefined. So if x is 0, well, that's not in the domain. It's a candidate for x equals 0 is a candidate for a vertical asymptote. You're dividing by 0. Oops. So the candidate here is x equals 0. Okay, so let's try to find these one-sided limits. So let x, let's say, approach 0 from the positive side. And think about how we can, well, are there any answers in chat, or anybody kind of see what's going on? Is this limit going to be infinite or not, or finite? Okay. So let's just chain our reasoning here. So as x goes to positive infinity, or sorry, positive 0 from the positive side, what can you say about 1 over x? What is it approaching? Okay, that's right. So looking at the graph of 1 over x, as x approaches 0 from the left, the graph here indicates that 1 over x grows without bound. So that goes to positive infinity. Okay, so now the 1 over x is just the argument of this exponential function. So as 1 over x goes to positive infinity, what can we say about e raised to the power 1 over x? Where would it go? Yeah, that's right. So we see that as the argument of our exponential function goes off to infinity, the function blows up. So we say that our exponential function goes to infinity. So that indeed is an infinite limit. Okay, from the right here. So we see that x equals 0 is a vertical asymptote. Okay, and then let's think about the other one-sided limit. Now we already know it's a vertical, x equals 0 is a vertical asymptote, but just for fun, let's analyze this limit. Okay, so same idea. So as x goes to 0 from the left, what can we say about 1 over x? What values does 1 over x, what value does 1 over x approach? Or, yeah, negative infinity. So you have, as x approaches 0 from the left, 1 over x we see goes off to negative infinity. And in turn, if the argument of our exponential function, namely 1 over x, goes to negative infinity, what do we know about our exponential? Where does it go? So as the argument of our exponential goes to negative infinity, our function is approaching, or our exponential function is approaching 0. Okay. So this one-sided limit is not infinite, it's 0. And before we move on to Squeeze Theorem, maybe just for kicks, what is the limit here? Do we have any horizontal asymptotes? Oops. So how do we attempt to answer this question? If the professor asks, does this function have horizontal asymptotes? In terms of calculus, what do we need to do? Well, we need to compute limits at infinity. So we're going to need to compute the limit as x goes to infinity. And then also, because we could possibly get a different, or maybe not even, we need to find the limit as x goes to negative infinity as well. Everybody's crying these days in chat. Okay. All right. So, I mean, that's the same reasoning. We see that as x goes to infinity, we see that 1 over x is going to go to 0, right? Because you get something like 1 over infinity. That's like 0 at the limit. And therefore, if the argument of our exponential function goes to 0, right? That goes to 0, we're going to end up with e to the 0, so 1. So here the limit is 1, so we see that y equals 1 is a horizontal asymptote, because you get a finite limit. And from the left, I believe it's the same argument, right? Sorry, as x goes to the left, it goes off to negative infinity. You see that 1 over x would go to 0 as well. So e to the something that goes to 0 is something that goes to 1. Yeah, so we have a horizontal asymptote in both directions. And that was just a graph of that function. So okay. All right. Okay, so that was infinite limits and limits at infinity. So let's move on to Squeeze theorem. So here, if we try to, so here's an example of a function. This is a iconic limit, right? It's going to be used in like finding or finding the derivative of the exponential function. Okay. So it's an important limit. What's interesting about it is that, like, none of the techniques you've learned so far really can help you evaluate the limit. If we evaluate directly or attempt to, we get 0 divided by 0. And e to the 0 is 1. Okay, so that's indeterminate. Okay, but none of the tricks like factoring, right, work because like this is not a polynomial; it's an exponential function. So you can't factor that. You can't. It's an interesting perspective to say that one of the factors is x. That would be interesting, but you can't factor because you're no longer dealing with polynomials, right? Okay, so here I'm going to use a different technique. It's going to involve the algebra of inequalities, but just without proof, let me do this, right? Okay. So I can prove, well, that this function is going to be bigger than this line of slope 1/2 and intercept 1, but it's going to be smaller than this parabola. So the graph of this quadratic is a parabola. Okay. Now that's true near 0. Okay. It's not true further away from 0. So eventually this exponential will become bigger than this quadratic. Okay. But we only care what happens near x equals 0 because we're dealing with the limit as x is approaching 0. So x is close to 0. Okay. So if I were able to prove, right, to you that our function is sandwiched in between a lower bounding function, so we have the line in green, then we have the parabola in green, and then our exponential is sandwiched in between. Okay. So now look at the limit as x approaches 0 of this line, if you will, this function, the left bounding function, and as x goes to 0 to be left with 1. And now let's look at the limit of the right bounding function. So that's the parabola in green. As x goes to 0, we're just left with, well, 1. Okay. So now you can maybe move that over. Okay. So maybe now you can kind of guess what we're doing here. Okay. So as x goes to 0, the left bounding function and the right bounding function both go to 1. They go to the same value. So if e to the x minus 1 over x is always stuck in the middle between the line and the parabola, okay, so if the limit of the smaller function and the big function is they're both 1, then the limit of our middle function has to be a number between 1 and 1, right? So that limit has to be 1, right? It's the only number between -1 and 1, inclusive. So what this example demonstrates is that we want to find the limit of some function that's not just a simple that, it's sufficient to use techniques for pre-calculus or something. So what we did is we squeezed our function between two bounding functions. And then we took the limit of all three functions, and the two outside functions had a common limit of 1, so the thing in the middle had to go to 1 as well. So that's called the squeeze theorem. What was the determinant? It was. So when we evaluated the limit directly, somebody asked us if they thought that this limit is indeterminate. It is. If you evaluate directly, you get 0 divided by 0. That's indeterminate form. So but because the limit was indeterminate, we found a new technique to determine whether the limit exists, and if it does, what it is, right? The idea is that to sandwich or squeeze our function between two others. And if the limit of the two outside functions is some value, then the thing that's in between, our function, has to go to the same value at the limit. No, some limits don't exist. So somebody asks, does it mean that, do we always have a limit for all functions? No. Sometimes the limit doesn't exist. Okay. So the squeeze theorem, again, you want to determine the limit of some function, our function. So what you do is you take our function and try to find two bounding functions. So here g should be smaller than f and h should be bigger than f near our point, x equals a, because x is approaching a. So it's a local phenomenon, right? And then we compute the limit as x approaches a of the two bounding functions, the bigger and the smaller one. And if those limits are the same, then the thing that's in between has to go to that same limit. Right? All right. All right, so let's look at this example. So here the problem is if you try to evaluate directly, and I mean, I guess you could guess what the limit is, right? If you evaluate directly. Oops. Well, you get something that's weird. I mean, you get 0 times something, but this cosine of 1 over something that goes to 0, this limit doesn't exist, right? Why doesn't this limit exist? Well, you get cosine just keeps oscillating, right? As x goes to 0, 1 over x will go to, well, plus or minus infinity, doesn't matter which one. But as the argument, right, 1 over x goes to plus or minus infinity, cosine just keeps oscillating. So this limit doesn't exist. So this is kind of like 0 times something that doesn't exist. This is nonsensical. Right. So instead, we want to use the squeeze theorem. And the first step in trying to find, two bounding functions. So we're taking our function and we're trying to find a lower bound and an upper bound. That's right. So what we want to start with is the fact that if you look at sine or cosine of theta, I mean, just again, look at their graphs, I suppose. But we know that the range of sine is between -1 and 1, right? So regardless of what input you put into sine, the output is always a quantity between -1 and 1. And the same thing for cosine. It doesn't matter what you put in. So these are popular choices, right, when using Squeeze theorem to start with sine or cosine, because every student should know that it doesn't matter what you plug into sine or cosine, you always get something that's bounded between negative and positive 1. Okay. Let me move that over. Okay. So that's going to be our starting point in constructing two functions, bounding R's. I don't care what x is. Of course, x cannot be 0, but 1 over cosine of 1 over x always returns a number between -1 and 1. So that's going to be the start of our inequality there. So now we're going to try to, what do we need to do to get our function in the middle? Well, it looks like we need to multiply the middle part by x squared. But we're going to just multiply everything by this positive quantity x squared. So multiply -1 by x squared, positive 1. So I just multiplied everything by x squared, right? So to speak. Okay. Get rid of that. So we started with a basic fact about sine or cosine, and then we multiplied everything by a positive quantity so that we get our function in the middle. Okay. So next, I find the limit as x approaches 0 of everything here. Okay. So we see that as x goes to 0, sorry for that's okay, minus x squared goes to 0. And likewise for x squared, that also goes to 0. So the limit of the thing in the middle has to be 0 as well. Yeah, the limit of x squared times cosine 1 over x is some quantity between 0 and 0, so it must be 0 by the Squeeze theorem. I won't go into it, but maybe on your own, you want to look at the graph of arctangent. If we have time, you can look at it, but arctangent of x. I mention it because that's another function that's bounded. If you want to recall or study the graph of this function, you'll find two horizontal asymptotes. Y equals pi over 2 and y equals negative pi over 2. So arctangent, like sine or cosine, is a function that's bounded below and above. So that's always also a good function to kind of work with when dealing with Squeeze theorem. All right. So now we're going to look at, you're going to use the Squeeze theorem to prove the limit of a special function, the limit of sine of x over x as x approaches 0 is, okay, so this is a shirt you can buy. This is a joke, by the way. sine of x equals x is a joke. It's not correct in general. It's not true for all x's, right? So the joke is that, it's like an engineering joke, that sine of x is very close to being x for small values of x. So for x is near 0. And that's useful, right, when you want to approximate stuff. So we see that this idea, this approximation is useful to anticipate what this limit should be, because x is approaching 0. We know that x is close to 0, so sine of x is going to be approximately x. And if now divide by x, you see that sine of x over x should be close to 1. So we guess that since the limit of that constant is the constant, the limit here should be 1. And this is correct. Okay. Now we want to kind of prove this, maybe just to practice our trigonometry. Okay. So we're going to prove this using Squeeze theorem. All right. So we'll use a unit circle to prove this. So we have the radius of the circle is 1. We're going to label this angle theta. Let's just say this is in green. Okay. So looking at this right triangle that we create, this is theta. Hypotenuse is 1. What is the length of this opposite side in terms of theta? How do we go about finding an expression that gives you the opposite side? Well, if we want to relate an angle to the side opposite that angle, we do want to use sine. So sine of theta is the opposite side divided by the hypotenuse. Hypotenuse is 1. So this opposite side has length sine of theta. Okay. Okay. And what is the length of that part of the circumference there that's in orange? What expression gives you this length? Okay. Oops. So if we have a circle of a certain radius, and you have this angle theta here, what we're interested in is this length. I'll just call it S. Okay, so it turns out that the ratio of theta to the total angle in a circle in radians, 2 pi. So 2 pi is, of course, the total measure around a circle. Would be the same as the length along that circumference divided by the total length along the circumference, i.e. the circumference. Okay. And if you do the algebra, we see that the length is simply r times theta. So radius times the angle, and we just have to remember that this angle is measured in radians. You have to be in radians to relate lengths to angle measures. Okay. So since we have a unit circle where r is 1, that length here is simply theta. Okay. So the length of the orange part of the circumference is theta itself. Now if you look at the blue segment. This is a segment that's tangent to the circle. And we know that segments tangent to a circle are always perpendicular, are always perpendicular to the radius. That's just a fact from geometry. So we have yet another right triangle there. Okay, so we have our radius of 1. We have theta. And now this side, we want to find an expression for this opposite side. Okay, so which, if we want to find the opposite side as expressed in terms of theta, which trig function would we want to use for the triangle in blue? That's right. We want to relate this angle theta to the side opposite, but we don't have the hypotenuse, right? We have the adjacent side, so we want to relate opposite to adjacent side. You'll use tangent. So tangent of theta is opposite over adjacent, which happens to be 1. Okay, so this blue part is tangent theta. All right, so now here this is not like a, well, this is without proof, but I hope you see that this green segment, sine of theta, is going to be smaller than the orange length, which is theta, which is going to be smaller than the blue length, the tangent of theta. What was a pun? Can somebody explain, if you're talking about a pun, what it was in chat? Okay. Tangent? Yeah. Oh yeah, that's literally the blue segment is tangent of theta. It's tangent to the circle, and so I guess that's maybe the way the name was derived. Okay. So now let's notice that if I just take sine of theta is less than or equal to theta, so I'm just working with this inequality, and then divide both sides by theta. Theta is not 0. Theta is going to be approaching 0. Divide both sides by theta, and we get that sine of theta over theta is less than or equal to 1. Right. So put that in our back pocket. So we're starting to squeeze our function between two others. Okay, spoiler. Okay. Now, if we take the other inequality where theta is less than or equal to tangent theta, well, and we want to get sine of theta over theta in there somewhere. So we're going to, towards that end, we can rewrite tangent as sine over cosine. And then we can notice that theta is positive here, and then cosine of theta is positive as well, since theta is in the first quadrant. So the ordering relation is preserved. Okay. So that's just rearranging, and we see that sine of theta over theta is bounded below by cosine theta. Okay. So I think we're ready to squeeze. Do you see how we want to find the limit of this as x or as theta goes to 0, and we've sandwiched our function between cosine theta and 1. Now, I would have to, of course, make an argument what happens when theta is negative, but we have 20 minutes, so I'll skip that part. But this inequality happens to work for theta, right? If it's negative or positive. Okay. And indeed, I was hiding a picture of that. So let's just look at the picture. So the graph in orange is sine of theta over theta. Then we have the function, constant function where y equals 1. And then we have cosine of theta. So at least near x equals 0, we see that our function is sandwiched in between the other two. And from the picture, we see that as theta goes to 0, all right. Right. So sandwich theorem says we next take the limit of everything. All right. So as theta goes to 0, cosine of theta goes to cosine of 0. Cosine of 0, we all know or will recall that is 1, and the limit of a constant is 1. So the limit of our function is a quantity between 1 and 1, namely 1. So that's a special trig limit. Okay. Anyway, if you know L'Hopital's rule, this is of course easy, but you're going to be using this without L'Hopital's in class. Okay, so let's look at some quick examples. All right, we're going to use the special trig limit to evaluate this one. Okay, so x is going to 0. So since x is close to 0, 5 times x is also close to 0, right? So using our engineering approximation here, sine of 5x will also be close to 5x. Right? Whenever the argument of sine is small, close to 0, that's something we can look at to get a sense of what's going on. So this will reduce to, will be close to 5x over x. Okay. So near 0, it looks like our function approaches is going to be close to the value of 5. So we anticipate this limit is 5. Okay. Now, to use the special trig limit, and this is going to be the moral of this problem, is that the thing that you see, the function that's inside the sign, okay, has to be matched by whatever is in the denominator exactly, right? So we want the denominator here to be exactly the same function as what's inside the sign. These must match. These match exactly before. Okay. All right. So what do we need in the numerator? Sorry, what do we need in the denominator here for the denominator to match the inside of the sign? Well, we need a 5, right? We need a 5x. But if you multiply, so you can introduce that factor in the denominator by multiplying the bottom by 5. But of course, we just don't want to change the expression, so we're going to multiply the top by 5 as well. So multiply the top and bottom by 5 in order for the denominator to match the argument of sine. And then, Okay, the 5 out here is a constant, so it's unaffected by the limit 5 times. And now you can use the special trig limit, but maybe more formally, we're going to let u equal 5x. Okay. And observe that as x goes to 0, 5 times x, or that is to say u, goes to 0 as well. So as x goes to 0, that's the same thing as saying u goes to 0. Okay, and now we know that this is our special trig limit. Sine of u over u as u goes to 0 is simply 1. So the answer is 5, as we anticipated with our close to 0 approximation. Okay. The moral being that if you want to use the special trig limit, the function that's inside of sine has to go to 0. And if that function is inside of sine, that's exactly the function that you need in the denominator before you get to use the special trig limit. Okay. This one's going to be quick and simple. So here, if you have a number, non-zero number, you can always write it as the reciprocal of its reciprocal. So for example, I can write 2 as 1 divided by a half. Okay. So I can take this fraction and just write it as the reciprocal of its reciprocal. And now the limit at the top is just 1, it's a constant. So we just have to focus at the limit at the bottom. But now you recognize this as our special trig limit, which will go to 1. Okay. So we just needed to point out that the limit of the reciprocal sine x over x is still 1, right? I mean, if this goes to 1, then why shouldn't its reciprocal go to 1 as well? Right. Okay. All right, and maybe if we have time. So let's look at this, and we're going to be using our special trig limit. But of course, I'm missing the sign. So what can we do so that we can use our special trig limit? What can we do to the top and bottom of this function? Any ideas? How can we get multiply by sine of x? Yeah, we could do that. But okay, here's a hint. So you all know this trig identity, the so-called Pythagorean trig identity, right? So rearranging this by subtracting cosine squared over to the other side. Do you know how to factor 1 minus cosine squared? Yeah, we're going to multiply not by 1 minus cosine. We're going to end up multiplying by 1 plus cosine, but that is the correct the approach there. So notice that this is a difference of 2 squares, so we know it can be factored into the product of conjugates. So 1 minus cosine and then 1 plus cosine. Okay. So we know that we multiply by conjugates if, for example, you want to get rid of square roots, right? If you multiply by a conjugate, you get a difference of 2 squares. So the first number squared gets rid of the square root minus the second number squared. That gives you 9. But another time you might think about multiplying by conjugate is when you see sine or cosine, right? Because that's going to allow you to use the Pythagorean trig identity. Okay. So here what we want to do is multiply the top and bottom by 1 plus cosine. Okay, because in the numerator you get a difference of 2 squares, so 1 squared minus cosine squared. Well, the denominator just is what it is. We'll not worry about that right now. But then that allows you to use the Pythagorean trig identity here on top. 1 minus cosine squared is sine squared. Okay. So now we get to use our special trig limit. So sine of x over x quantity squared times 1 over 1 plus cosine x. So sine of x over x goes to 1 as x goes to 0, special trig limit. And then this denominator here, as x goes to 0, cosine of x goes to 1. So you're left with 1/2. Okay. All right. I don't think we'll have time for another. Well, let's do this one real quick. Okay. All right. So we talked about the special trig limit. That's one. Can we? But what would the limit at infinity be here as x goes to infinity of sine of x over x? Can we, for example, use this approximation sine of x is equal to x or close to x? Can we use this approximation here? We cannot use, right? Why not? Well, because this works for small x's, but x is definitely not small if x is going off to positive infinity. Okay. So we can't use this approximation. We can't use the special trig limit because x is not going to 0, it's going to infinity. So what can we use? Well, some sort of squeeze idea, right? So if I said use a kind of squeeze theorem at infinity, so as x goes to infinity, what's the starting point for using squeeze theorem here? Well, you start with the fact that sine is a function bounded above by negative and positive 1. And then you might want to divide everything by x, which is fine. X is positive here. And then take a limit as x goes to infinity. And we see that the two outside functions go to 0 at infinity. So this Sine of x over x also must go to 0 at infinity, right? So, I mean, the idea is simple. Sine keeps oscillating, and then you think of that divided by x as like an amplitude. 1 over x is multiplying sine, so that's like a variable amplitude for your sine function. And this keeps oscillating. I might misspell oscillates, I apologize. Okay. And so if you have a sine function that keeps oscillating, but the amplitude goes to 0 because 1 over x goes to 0 as x gets large, you get something with decreasing amplitude. So you see that as x gets very large, our function is approaching the value of 0. Anyway, Elliot posted a link to a survey if you want to do that. It's the same one as yesterday. Leave your feedback, and thank you for being here. And we'll see you tomorrow. We'll be talking about derivatives. And what else? Continuity and derivatives. Elliot and I will both be we'll be doing a section. So anyway, we'll see you tomorrow. Follow the link, and we'll talk about derivatives and continuity and possibly tangent lines. Yeah, I'm gonna post. I'm gonna after it gets all processed and stuff, I'll maybe do a little editing, cut some stuff out, make any corrections, but I'll post it on YouTube tonight. It'll be on our peer tutoring UTD YouTube channel, and we'll see you tomorrow, right? And I'll leave somebody. If you want a puzzle, I'll leave a puzzle. By the way, okay. This is a propos nothing except maybe the trig identity. So this maybe this puzzle can be solved using this Pythagorean trig identity, and maybe something about the first quadrant of the plane. And here's the question. What is the sum of sine squared of 1 degree, sine squared of 2 degrees, so on, all the way through sine squared of 90 degrees? What is the sum equal to? It's a puzzle. Good luck if you want a puzzle.